Okay, so this is our chapter 7. So chapter 7, we're going to learn the digital arithmetic and arithmetic circuit. So this is different from controller design. So when we talk about digital control, we write in HDL to control a digital device. A lot of time we use hardware programming for digital arithmetic. So normally we can do digital arithmetic in general PC. What is the benefit of doing it using VHDL instead of just writing C code or Python code? That is because the most important applications of FPGA, or I should say one of it, is acceleration. When we talk about acceleration, this is called hardware acceleration. So when we run an arithmetic or computing on the FPGA, it can run faster than a general PC. So we call it a hardware acceleration. So if we want to run this algorithm on the FPGA, we have to write the digital arithmetic code to do the computation. So that is why we are learning it. And again, if you can relate this to general PC, it's the same. So general PC, it has hardware, it needs to do every computation in hardware. So we are learning all this background knowledge about this hardware computation. So digital arithmetics, when we talk about this, we are going to talk about binary values, hexadecimal values, and the most important device or elements that we use in digital arithmetic is actually very simple. It is the adder. It is adder. So anything else, all the other computation can be derived from the simple adder. So this is what we are going to learn in this chapter. So when we talk about binary numbers, now we know how to convert decimal numbers, binary numbers, hexadecimal numbers. So among these different number types. So in binary numbers, we have signed and unsigned. This is similar to our decimal number. We have positive, negative. So binary numbers, when it's unsigned, everything you can treat it as a positive number. So without a sign. If it's signed, then we will have the sign bit, which is usually the most significant bit, a single bit. Because for the sign bit, for the sign of the binary number, it can be only one of two things. Either is plus or minus. So we use one single bit. One single binary bit gives us two options, 0 or 1. So 0 indicates that is a plus sign, so it's a positive number. Minus indicates that is a negative number, so it's a so this is the sign bit of a signed binary number. So apart from the sign bit, the other bit will be the magnitude bit. So if it's an unsigned binary number without a single bit for the sign bit, all the bits will be used for magnitude bit. So the unsigned binary arithmetic is simple. So we don't need to worry about the sign bit. So for sum is the result of an addition of two or more binary numbers. And there is a carry bit. So the carry bit is a digit that is carried over to the next most significant bit during an n-bit addition operation. So the carry bit is when if the result was too large to be represented by this n bit. So we use the carry bit in decimal arithmetic all the time. let's say you want to multiply 9 with 8. So you the result is 17. So 17. So how do we come up with that? Because 9 plus 8, there will be a carry bit. So we count. So the maximum values that we can represent in decimal numbers. So it's 9. So if we add 9 with adding other numbers from 1 to 9, it will end up with a carry bit. So let's say 9 plus 1, it will give us 10, which needs 2 decimal bits to represent. So that is the carry bit. A carry bit is used to carry this overhead that can't be represented by this the n bits value we have. So it's going to be carried to the next bit. So this is the example of 1-bit unsigned addition. So let's have a look at the example we have here. So we have carry bit in and carry bit out. These are different. So this is the carry in bit is from those bits that has a smaller weight than A and B. Let's say if we have so our class number 384, okay? So if I want to add 384 with 20, so add 384 with 20. So that means the carry in bit for the middle bit. Let me put this note on. Okay, so let's do this 384, and I want to add it with 20. Okay, so add with 20. So the last bit here, hopefully you can see this. I think it should show on these slides. So 384 plus 20. So 4 plus 0. This will end up with 4. Okay, so let's do this. And this last bit will be 4. So there is no carry bit, no carry out bit for the last bit. That means for the middle bit here, 8 and 2, so there will be no carry in. So now you know this carry in is this carry bit from the previous, the lower weight bit. So here we will got no carry in for this 10th bit here in this decimal value, but 8 plus 2, it will end with 10. So for this one, this 10th bit is 0, but we end up carry out. So carry out for this bit is 1. So we have a carry out of 1 to the next digit, not bit, okay, to the next decimal digit. So we will have a 4 there. So in this example, we have for the so 10th decimal bit, we don't have a carry in, we have a carry out bit. So this is what we have here as a carry in, C step in and C step out. This is a carry out. Sum is the result of result of the addition of that decimal. So this is an example of the decimal addition, unsigned decimal addition. Now we have a look at this binary example. It's the same. You just have to remember in decimal we have 0 up to 9. In binary we have 0, 1. So whenever we have 2, there will be the carry bit there. So for the first row here, 0, carry in 0, A and B are both 0. So we end up with a 0 carry out and 0 sum. So for the second one, so 0 carry in, A is 1, B is 0. So the sum will be 1 and carry out will be 0. Third row, we have carry in is 0. A and B, they're both 1. So we add these two together, it will be 1, 0. So A and B added together is 1, 0. So the sum bit is 0, but we will have a carry out bit of 1. So there is 1 carry out bit. Okay, so let's have a look at the last example. We have carry in is 1, A is 1, B is 1. So these three added together in binary is 1, 1. In binary is 1, 1. So we have 3 actually. So we will end up with the sum value of 1 and a carry bit of 1. So that is 1, 1. And you know this 1, 1 in binary is 3. So that actually works out correctly. Okay, so this is the unsigned sum, and this is the simplest arithmetic element in digital electronics. So it's a very simple concept, but it's actually very important. And normally we call this as a half adder. And what is a full adder? You will see in a minute. Okay, let's read this and move on. Okay, so a more more complicated example. Okay, let's have a look at this. See if we have grasped the concept. So 1 0 0 1 0 plus 1 0 1 0. So you align them together like this and add it. So let's have a look at this 0 0 add together is 0. 1 and 1 add together is 0 with a carry out. So this carry bit will be moved here. Carry bit will be moved here because this is 0 0. So the carry bit will fall to the result. And the next bit 0 1 add together is 1. There is no carry in and no carry out for this bit. And the last bit just fall down here as 1. So this is simple. Have a look at the example on the right side. We have 0 1. So you may have noticed we always work from the left side to the right side, sorry, to the left side, because the right side is the least significant bit, and the left side is the most significant bit. So 0 1 add together is 1. There is no carry out. The second bit 1 and 1, the add together is 1 0. There is a 0 sum here, but 1 get carried into the next bit. And this effect is the ripple carry effect. So we carried 1 over with the previous one. It ends up with 0 sum and carry another 1. Okay, carry another 1 here. So another 1 add 1. There will be a 0 sum with another 1 carried over. So this 1 carried over with the original 1 end up with another carry 1. And then that one with this one, we will have another 0 sum and carry 1 over. So this one is actually carried all the way through the beginning, through this second bit to this bit here. So it's a ripple carry. And the last bit, the most significant bit, these two 1 add together, we have a carry out, so 1 0. So hopefully this is still very simple to comprehend.